All right. So this is the OMRON C28H. Um, you can see here in my picture, um, you've got your inputs on the bottom of the card. Now these modules, this is the CPU module. So the CPU is capable of 16 inputs, and then you've got your outputs up here. And these numbers correspond to the internal registers in the device. And that's what we're going to go over, because this controller right here, this programming console, this is the only way to program and monitor the logic inside of the unit. And it's as you can see my little emoji here, this thing is not very fun to work with. And it's we'll get into it here. So this is an example of a ladder. The column at the right is going to be what you're going to see, but you only see that one line at a time. For instance, 0000 LD is load. That's what that stands for. And that's loading input 0, the very first input of the device. So that's that first line there that you're saying. So this is what a ladder will look like once we extract this information and then translate it. Now, there's no tool to do this, right? So this will all be manual ladder creation, but this is what it looks like. So for one ladder inside this PLC, this is what an example of what it looked like. Now, this is called mnemonic code, mnemonic. And this is the definition of mnemonic code. It's a short and easy to remember set of letters, words, or phrases used to represent something more complex, often as a memory aid. In computing, for example, assembly languages use mnemonic code. Now, I found it quite funny. I hadn't really ever referenced mnemonic code before, just because the current PLCs are everything's done for us, right? Everything's become very simplified. So I don't really have to worry about binary or mnemonic code or translating anything. Everything is kind of laid out in ladders for us already, right? So there's a little bit of sarcasm in this class, just because it was very frustrating to work through the 367-page manual and try and figure this thing out. So this covers our internal relay bits and words, right? So this is the reason this is important, is because as in this first picture, this data point right here, these are all going to correspond to internal relay bits or words within the unit, and we have to know what they stand for and what they are. So I've attached this little page right here a couple of times throughout the presentation, because we're going to have to understand what each one is each one of them means. So IR stands for internal relay. SR is special relay. AR will be our auxiliary relays. DM is our data memory. HR are our holding relays. LR are our link relays. TC, those will be our timers and counters. TR is temporary relay. And UM is program memory. Now, work bits and words. So when some bits and words in certain data areas are not being used for their intended purpose, they can be used in programming as required to control other bits. Words and bits available for use in this fashion are called work words and work bits. So to me, this is like an internal thing. So you're gonna go ahead. Oh, somebody must have just jumped on. So this gives you the ranges of each one of the bits and words that you're able to use, right? And kind of what this is going over is, if we're not using them for an input or an output, they can be used internally, right? So if we want to fire a coil, oh, here it is, right? So this coil 500, that doesn't correspond to an output. That's an internal register that we are able to use. And out not means it's going to be on all the time until this becomes true. But this is something internal that we would use. So if we're, you know, we're needing to use this status of HR1, whatever that might, HR15, somewhere else in the program, this coil will be used internally within that program, right? Flag and control bits. Some data areas contain flags and or control bits. Flags are bits that are automatically turned on and off to indicate particular operation status. Although some flags can be turned on and off by the user, most flags are read-only. They cannot be controlled directly. Control bits are bits turned on and off by the user to control specific aspects of operation. Any bit given a name using the word bit rather than the word flag is a control bit. So restart bits are control bits. This is our data area structure, right? So we went over a lot of these, and I'm attaching it yet again, right? Because it's very important when we're going through each single line of this device that we understand what each thing does, because we'll have to translate it, okay? So when designating a data area, the acronym for that area is always required. But the IR, internal relay, and SR, special relay areas, are acronyms for the IR and SR are also given for clarity in text explanations. They're not required and not entered when programming. So, you know, those are some of the things that we're not going to see necessarily in there. It's just basically telling us that you don't have to have the acronym for them in to use them, right? You'll go off of their word range, 0 to 246 or 247 to 255, and this is the bit range. And how this bit range works is, I think it's the next slide we start going over this. But so I'm not sure if you guys are familiar with words and bits, right? But in this PLC, they only use integers, so they use a 16-bit word, right? And this is telling us right here, IR starts at 0 and it ends at 246. So there's 246 words of internal relays. Now, if we want to specify the very last word and the very last bit in that word, that's what this is showing us right here. So 0 to 24615. So when we look in that LCD display, if we're using a bit out of that word, the word is on the leftmost part, right? Because we only have 5 digits that we're able to look at on the LCD. So the word is going to be 246, and 15 corresponds to the very last bit in that word. Does that make sense so far?
Yes.
Okay. And you don't have to fully understand everything. You know, it just I have to fully understand it because I'm going to have to decode it. But we need to go over it so you have an understanding of what's going on and what we're going to be looking at, because this PLC will be the second PLC that'll be replaced. It'll be quite a bit of work to get this where it needs to be. This is that data area structure. So this is showing you like an internal relay word, and here's your bits. And this kind of explains it, right? So this shows all the other acronyms here, each of which consists of 16 bits numbered 0 through 15 from right to left, not left to right, right? So our right to left. IR words 0 and 1 are shown below with their bit numbers. That's basically all this is showing here. And yet again, I put this acronym cheat sheet here so that you can get used to the acronyms within the device, because we'll be going through it in some aspects. This is where I spent 8 hours of my time trying to figure out what was going on here. So this is an explanation that they have on page 14 out of that 369. Okay. And this is kind of showing us if you have an internal relay 00, the leftmost bit in the word is 0. So that's the first bit. And the rightmost would be 15. So that's our bit designation. And then you can go down to, you know, your special relay here. So 252, that's the word 252. And then the rightmost is 0. So that's the first bit in word 252 of special relays. Data memory, it's showing you an example of what's not possible, 1250, right? And if you look up here, our data memory only goes to 999. That's why that's not possible. Tracking so far? So
Yes.
TC, timer counter, 215, designates a process variable. So that's within that. So that's a bit origin. So 215 is it's a completion flag for a timer. And this is where I got hung up. So link relay. This was the example that was given to me. So link relay word 45, bit designation 1200. Now I'm not kidding. I spent 8 hours trying to figure out what this meant and how it was going to translate. It just doesn't make any sense. And there's a reason for it. And 8 hours later, plus another 4 hours for email with OMRON, they don't make the product anymore, but they were willing to look at the manual for me on that specific page. And this is the email that they sent me. This is a better explanation of the memory area, which I've been going over. Seems like the table I mentioned was not correct. So I got hung up on that page. I'm not kidding, for literally 8 hours between 2 days. This is a better explanation of link relays. So that was incorrect information in the manual. Very frustrating as you're trying to go through something. And you guys might be asked on a regular basis to go through manuals for a new device, a new piece of hardware, right? And this is kind of just showing how much detail I put into reading through these manuals and trying to learn the device itself, because really that's all that separates us from the guys that aren't doing the work that we're doing is how far we're willing to go and how deep we're willing to dig into the device we're looking at, because we don't understand the hardware all the time. We don't necessarily know all of the endpoint devices, right? But being able to learn them and figure them out is part of this job. So I just found it at this point in the training manual that I was creating, I was fairly frustrated. But we'll move on. Now we have a good explanation of what's going on in here, our link relays and our acronyms that relate to all these words and bits. So our internal relay area, this is important for us because in the field, in the unit that we're going to be working on, we do have one CPU and it also has 2 expansion units. And this is important because our internal relay words that correspond to those input and outputs, right, are going to be shown right here. This is straight from the OMRON manual itself, of course. But so, for example, our input words for the CPU will start at 0 for our C28H. And so we'll have 0 through 15, right? Because then the CPU unit itself only has 15 inputs. And our output words will start at 2. So that'll be on our leftmost column of our 5-digit mnemonic code. And then on the right side, it'll be broken out by bit. And they're in the 200s range, starting with the CPU unit. And then once we move on to our expansion units, because the one main CPU has all the program in it, we'll start seeing our input words on word 10 on the first and word 20 on the second unit, right? So we have 3 total units to decode and go through. And I can go through this whole thing, but that basically explains the same thing, right? So here's an example I put down here. So second expansion unit output 5 would be out 2205. First expansion unit input 3 would be 1003, which 10 is corresponding to our word, 3 is corresponding to the bit for output 3. Same here. Second expansion unit word 22, bit 5 would be output 5 for the second expansion unit. Understand?
Yeah, that makes sense.
So there's no I/O wired to the CPU module?
There is.
Wow. Okay.
There is, and then that corresponds to our CPU right here. So that'll be your first word is 0 for input words and 002 for output words.
Thank
The following tables show the I/O bits used for each of the CPUs and expansion I/O units. For the expansion I/O units, IR10, 20, or IR30, depending on, and I just kind of went over that, right? So this just kind of just goes over it in a little bit more detail, and corresponds to the IR, depending on what unit it is. And I just highlighted, our units in particular, the C28H. There's your output bits, how I said 200. So we've got 11 outputs on the C28H unit. So this is where we start decode and ladder basics. So this is a basic ladder, right? And it's quite funny to read some of these older manuals. We're pretty familiar nowadays with ladder diagrams, but this kind of lays it out for us. A ladder diagram consists of one line running down the left side, as you can see here, right? This is true to today. Branch with on the left side with lines branching off to the right, which I would call rungs. Okay, so this totality, this is a ladder, and then you have rungs on that ladder. Along the instruction lines are placed conditions that lead to other instructions on the right side. So our logic follows from left to right. The logical combination of these conditions determine when and how the instructions at the right are executed. And this kind of shows that. So you've got different different instructions here, right? So if we look at 0, 0, we know that 0, 0 is going to be that's going to be our first input, right, on our CPU. And if you start looking across, we have a lot of different types of inputs that we can use, and they're using a bunch of different things here. So link relays, holding relays, internal registers within there, and then instruction is corresponding to something they would do. They didn't finalize the ladder in this example, so you don't have a coil or you don't have anything that you're actually eventually finishing, but basically it's just the flow of water if you're familiar with ladders. So if this is true and this is not true and this is true, so on and so forth, at the end, if those valves or gates or whatever you want to call them, those instructions are true all the way to the end, then it's going to fire your coil or your instruction, your move function, whatever it might be. We're going to go over the very each instruction kind of individually. So these are your normally open and normally closed conditions. So like I was explaining, each condition in a ladder diagram is either on or off depending on the status of the operand bit that has been assigned to. A normally open condition is on if the operand bit is on, off if the operand bit is off. A normally closed condition, shown in the bottom picture here, is on if the operand bit is off, which means, so if we're not seeing that status come in, it's going to be true here. So we can use it either way in our program depending on how we use our operand, right? Normally open or normally close. And when those are true, regardless of the state it's in, you can pick whichever way to use it in the logic. Your instruction is going to be executed. In ladder diagram programming, the logical combination of on and off conditions before an instruction determines the compound condition under which the instruction is executed. This condition, which is either on or off, is called the execution condition for the instruction. All instructions other than load instructions, that's our LD, have execution conditions. Operand bits. The operands designed for any of the ladder instructions can be any bit in the IR, SR, HR, AR, LR, or TC areas. This means that the conditions in a ladder diagram can be determined by IO bits, flags, work bits, timer, counters, etc. Load and output instructions, which you'll see that coming up here, can also use TER area bits, but they do not, but they do so only in special applications. Now, as we go through more of this, I'm really hoping that they're using very basic ladder instructions just to turn things on and off, because these units are very powerful and they're capable of very complex ladder logic, and we'll go through that. But a lot of our stuff is going to be loading, and then our operand bits, we're going to be watching inputs and firing outputs. That is my hope, and we will find out on Tuesday if that holds true. So logic blocks, and this will have some examples of logic blocks. The way that conditions correspond to what instructions is determined by the relationship between the conditions within the instruction lines that connect them. Any group of conditions that go together to create a logic result is called a logic block. Although ladder diagrams can be written without actually analyzing individual logic blocks, understanding logic blocks is necessary for efficient programming and is essential when programs are to be input in mnemonic code, which is, we're going to have to go backwards, right? So we have to understand how they're writing this in mnemonic code. It's going to be very interesting to see how they chose to write the logic. There are multiple ways to write it and achieve the same outcome. So it really depends on the person that designed it. This is our program structure. The program is input into addresses in the program memory. Addresses in program memory are slightly different to those in other memory areas because each address does not necessarily hold the same amount of data. Rather, each address holds one instruction, like we were looking at in the example, and all of the definers and operands described in more detail later, required for that instruction. Because some instructions require no operands, while others require up to 3 operands. Program memory addresses can be from 1 to 4 words long. Program memory addresses start at 0 and run until the capacity of program memory has been exhausted. The first word at each address defines the instruction. Any definers used by the instruction are also contained in the first word. Also, if an instruction requires only a single bit operand, which those are going to be like inputs, outputs, and we'll use them for internal stuff as well. With no definer, the bit operand is also programmed on the same line as the instruction. The rest of the words required by an instruction contain the operands that specify what data is to be used. When converting to mnemonic code, all but ladder diagram instructions are written in the same form. One word to a line, just as they appear in the ladder diagram symbols. An example of mnemonic code is shown below. I don't know if I put that in here, but we're going over that mnemonic code, right? So this is an example, another example of a rung, right? And this is what it looks like, what we'll see line by line. And I've created an Excel file so that we can document this through down. But if you start here at the first, I've mentioned load multiple times. So load corresponds to the first rung on the ladder. Well, it doesn't necessarily to the first rung, but in this case, when we're starting at 0, it's going to be the first rung, and that'll connect to the leftmost part of the ladder. Okay, and then we're using our acronyms here. I can't even remember myself. That's why I put it in here 4 times, but HR001.
Holding relay.
Then we hold, there you go, holding relay 1, and or load not, and we'll start to go over what these load knots do. So the load knot it can be another attachment to the leftmost part of the ladder itself. And we'll get into some explanation or some examples here so we can kind of see it a little bit better. The address and instruction columns of the mnemonic code table are filled in for the instruction word only. For additional data lines, the left 2 columns are left blank. If the instruction requires no definer or bit operand, the operand and column is left blank for the first line. It's a good idea to cross through any blank data column spaces. So we'll leave, those spaces in there if they require data so that the data column can quickly be scanned to see if any addresses have been left out. When programming, addresses are automatically displayed and do not have to be input unless for some reason a different location is desired for the instruction. When converting to mnemonic code, it's best to start a program memory address 0, which when you use the programming interface, it starts at 0 when you're monitoring anyways, and you just have to go down line by line and read it. So we're getting into examples of really simple instructions or simple ladders, right? So this here, yet again, I'm showing you your LD, which is load, and that's 0. So when you type in LD, or when we look at LD, what that corresponds to, 000 is that first rung, and load 000 means that we're looking at this right here. Okay, and 001 is going to correspond to an instruction, which doesn't exist in this example, right? And when we hit load not, we're looking at a normally closed contact. It's loading it from the right-hand side. So that's what the ladder would look like if we translated those 4 lines. Is that, I mean, this is the most basic of basic starting right here. Everyone get this part of it.
Yes, makes sense.
Okay.
Yes, sir.
That's like the basic starting of the rung is the load all the way to the left.
Right, and that's the most basic thing that we could find in this PLC. I mean, there would be something at the end rather than nothing, right? There would be some kind of instruction output, internal coil. There would be something at the end, but that's about as basic as it gets. And then the only difference would be is, you know, here on 001, you would have a LR relay, and then let's say it's 205 or whatever, right? So for output 5. This is showing us when 2 or more conditions lie in series on the same instruction line. The first one corresponds to a load or load not instruction, and the rest of the conditions to and not instructions. The following example shows 3 conditions which correspond in order from left to a load and not and instruction. Again, each of these instructions requires 1 line of mnemonic code. So let's look at it again. We're starting at address 0, which is the very first part of our program. We're loading 0. Now that's normally open. Just LD load normally open. Load not would be this, right? So let's start load 00 and not, which gives us a normally closed instruction 100, and link relay 00. See, we're going and. It would be and not if it was normally closed. And then the last part is instruction. So that's where we would put, you know, our coil or whatever it might be, right? I don't know. I'm not really sure why they didn't give examples of our end instructions, maybe just because they start going over it later. But this is an example of and logic on a rung. When 2 or more conditions lie on separate instructions, lines running in parallel and then joining together, the first condition corresponds to a load or load not instruction. The rest of the conditions correspond to or not instructions. The following example shows 3 conditions which correspond in order from the top to a load not and or instruction. Again, each of these instructions requires 1 line of mnemonic code. I don't know why they keep repeating that like it's something super simple, but here is yet again 0 load 0. So that's your input 0, or not 100, or LR 000. Now, the only thing that I think this might be an error in the, because I think this is wrong. So we're loading right here. So it would be a load not if we're wanting to look for normally closed. This doesn't surprise me that I'm reading this now, but load would be 000. Yeah, see, I mean, your or instruction looks right. That's incorrect.
It'd be a normally open contact if it was LD.
It would.
Yeah,
So,
just like that and example that you had earlier.
Yep. So I'd love to get a hold of the guy that made this manual. So this is or instruction, and now we've kind of, and hopefully you guys are following along, because I mean, this is my 4th time reading it, and now I'm seeing it, but that's incorrect. Now we understand kind of what's going on when we're looking at these instructions and these operands within there.
So the take-home message is every time you have a load or load not, that means it's a new rung or a beginning of a rung.
Yeah, basically, yes. Here, this is an and or, and is taken between the statuses of IR0 and IR01 to determine the execution condition for an or with the status of IR200. The result of this operation determines the execution condition for an AND with the status of IR002, which in turn determines the execution condition for an AND with an inverse, i.e. and not, of the status IR3. Now let's start with our other instruction here. So we've got load 00, so there's that normally open, that's what it should have been on the last page, and 001, so we're putting in that 001 there, or 200, which puts in 200 right down here. So it's these two or 200, and which will put the ladder out here 002 and not 003. So that's kind of what that looks like. Now you can see here we didn't have another load, we just had an or after our first two instructions. And it kind of gave us this branch here. And this could be, you know, a seal-in circuit or something similar to that, right? The 200 is an output, right? So I don't know why they didn't just put coil 200 here and this would seal it in. And then when you lose any one of these inputs, that would be a typical seal-in, right? So, but that's the and or. So here's our input and output knots. So these are our output coils. The simplest way to output the results of combining execution conditions is to output it directly with the output and output knot. These instructions are used to control the status of the designated operand bit according to the execution condition. With the output instruction, the operand bit will be turned on as long as the execution condition is on, and it will be turned off as long as the execution condition is off. With the output not, it's the opposite. I don't have to read the whole thing. So this coil will not be on. 200 is not going to be on this load unless input 0 is on. In this case, it'll be opposite. This will be on. This output 201, which is the second output in the unit, is going to be on all the time until we get input 1. Or I guess, yeah, 0. This is input 0. This is input 1. So thought it fitting to put our end instruction here is because this is what we'll be searching for tirelessly on Tuesday. This is where this completes the ladders. This is the last instruction required to complete simple program is the end instruction. When the CPU cycles through the program, it executes all instructions up to the first end instruction before returning to the top. So start at the top, all the way to the bottom to our end instruction, and back up. In the device that I purchased, which does not have any secondary modules that go with it, there was 165 lines. So I'm hoping that we'll get somewhere similar to that or less. We'll see, with 2 extra modules included. But this is what it looks like, the end 01 right there. If there's no end instruction anywhere in the program will not be executed at all. So, and we don't necessarily have to worry about it. It's just more informational than anything else. We're just going to extract the data. We need to understand what it's doing to some extent. This is an AND load. So logic blocks, this is what they were talking about before. This is what they're calling their logic blocks. They do not correspond to specific conditions on the ladder diagram. Rather, they describe relationships between logic blocks. The AND load instruction logically ANDs the execution conditions produced by 2 logic blocks. The OR load instruction logically ORs the execution conditions produced by 2 logic blocks. Although simple in appearance, the diagram below requires an AND load instruction. So we're just looking here yet again. We're loading 01, which is our normally open, right? Or we're loading 01. There's our first block. And then we're hitting load again here, 002 or not 003 and load. So that and load is what's tying them together on that first rung right there. Okay, so that's how the and load is going to combine those two rather than starting a new rung.
So that means the load instruction doesn't necessarily signify it's a new rung.
It depends on the rest of the rung. Yes.
Because you would have to see the instruction part.
Yes. Yeah. Further down in the if you keep going down and you have an and load, then they're doing this. And this is, you know, this is showing that, you know, we could have 001 and this branch right here, which we could have 01 and 02 on to land the execution, or we could have 001 on and 003 off, or 001 on, 002 on. You see how that it just follows the flow, right? But that's how they're doing this. And like I said, I really hope that a lot of these are just push button controls, but we're about to find out. Following diagram requires an OR load instruction between the top logic block and the bottom logic block. An on execution condition would be produced for the instruction at the right, either when IR001 is on and IR001 is off, kind of like I was showing. When IR002 and IR003 are both on, the operand or of the OR load instruction and its mnemonic code is exactly the same that for an on load and load instruction, except that the current execution condition is ORed with the last unused execution condition. So yet again, we're starting here, load 001 and not 00 and 01, load again 02 and 03, OR load. That OR load is right here. It's that vertical connector at the end. So we could have either or condition, either or of those two conditions to execute our instruction.
So one could say the actual load command, all that means is it's going to hit the rail on the left.
Yeah, I guess so. Yes. Load. Yes. This is showing logic block in series. The code diagrams with the logic block instructions in series, the diagram must be divided into logic blocks. Each block, and this is what I said about there's multiple ways to do this, and it'll be interesting to see how they did it. But some might be a little bit easier to read than others. Each block is coded using load instruction to code the first condition, and then AND load or load is used to logically combine the blocks. With both AND load or load, there are two ways to achieve this. One is to code the logic block instruction after the first two blocks and then after each additional block. The other is to code all of the blocks to be combined, starting each block with load or load not, and then code the logic block instructions which combine them. In this case, the instructions for the last pair of blocks should be combined first, and then each preceding block should be combined, working progressively back to the first block. Although either of these methods will produce exactly the same result, the second method, that of coding all logic block instructions together, can be used only if 8 or fewer blocks are being combined, i.e. if 7 or fewer blocks instructions are required. The following diagram requires AND load to be converted to mnemonic code because 3 pairs of parallel conditions lie in series. The 2 means of coding the programs are also shown. So this is showing the 2 different ways we could achieve the same result. So let's start on the left-hand side example, and that's a load instruction 00 or not 001, which puts that right down below it. Load not 002 or 003, and load 004 LD004 load or 005 and load output 500. And then this is the same, we can do basically the same thing over here. It's just a little bit different. They're using that load instruction rather than the AND load. So load 001 or not 001, load not 002 or 003, load 004 or 005, and load. That's how they're combining. And I'm hoping they're not doing this. It'll be a little bit more confusing for me, quite frankly. This kind of breaks it down a little bit easier so I can see what's going on.
Yeah, I guess I was wrong. I thought the load meant that it was hitting the rail, but
And it really depends on, yeah, it really depends on the rest of the instructions, right? That's where it's, you got to see the whole instruction all the way to the end. Basically, what you're looking for is the out, and then you can, or the instruction. right? So whatever you want to execute in the end, and then you have to decode it from it within.
So your rungs are always going to end with an out or an instruction.
I believe so. Yeah. I mean, you have to have something at the end of it, right? So eventually you should have that out, and that'll basically be where we break that instruction. And typically what I seen in this program, at least here, is you have some kind of they've all been out so far rather than instructions, which is probably what we're going to see. And then right directly after that out, it starts with another load, which would, to me, correspond to another ladder, or another rung, I should say. Following diagram requires OR load instruction to be converted to mnemonic code because 3 pairs of conditions in series lie in parallel to each other. And we'll look at this left-hand instruction. So we're loading 00 and not 001. Then we have our load not here, 002, load not and not 003, normally close instructions. OR load connects us down here. Load 04, that looks incorrect as well. They put 40 instead of 4. And 5, OR load ties them together, and there's our output. So, and the reason I'm going over this, I'm still going to have to go over it more myself, but this is going to be quite the task. Whereas in the Gould, we had a visualization of the instructions and the operands. Mnemonic code is something that only savants or geniuses, in my eyes, can. Trying to translate this to straight ladder is going to be a little bit of a struggle. And I just have more examples in here to show us kind of what these things are looking like. Different ladders, load 06 and 7, or puts us around those two. So that's 005 and 3, which puts it in front, and 4 puts it in front again. Then we're loading again, 01 and 02, and our OR load ties it in around here. And 000 is at the end with our output LR, link relay 0. Another instruction here, I don't necessarily need to keep going through them, but you'll be able to reference this if you want to read it again. It's just another explanation. This is how they break it down in their blocks here. They did bring up blocks quite a bit, so it might help us compartmentalize some of this logic a little bit easier. Here's multiple instructions. This is an example of multiple outputs on the same rung, which at least in the OMRONs, the coils aren't stacked in front of each other and also used to control other parts of the ladder. At least the ladders are more contemporary. They're a little bit more straightforward when it comes to ladder form and function. Let's get into the keyboard. So this is, I highlighted this part because this is kind of important. The numeric keys, there's 10 white keys to input numeric program data. The red clear key, this is interesting. When you plug the unit in, it's going to pop up password, right? And any programming console operation can be canceled by pressing the clear key. Although the clear key may have to be pressed 2 or 3 times, which that is true. So basically when I get that password, I just hit the clear key 2 or 3 times, and then I hit the CHG button 2 times to get into monitor mode, and then I can scroll through. The yellow keys are used for writing and correcting programs, which is that, the CHG button is one of those, except the shift key in the upper right, the gray keys are used to input instructions and designate data area prefixes. Now, we're not going to have to be entering anything in. Mainly, you need to know that the clear key will get you out of basically whatever you're doing, right? It'll cancel whatever you want to do. And you might have to push it 2 or 3 times, which they even put in the manual. These are the different keys on there. And we're not going to be pushing any buttons other than the up and down arrows and the clear button. Those are the only buttons that will be pushed. Our key will be in monitor mode, and we do not want to change anything. So this is just for reference more than anything else. These are those PC modes, and I've highlighted our monitor mode here. So it's going to allow us to visually monitor in progress program execution. So we'll be able to see the statuses as well, like if something's on or off, which we can see on the lights as well. You generally used for trial system operation and final program adjustments. And you can change things while in monitor mode. So we just got to be very careful. Just like we were on the Gould, you can change things when you're in monitor mode. You just want to be careful that we're only pushing up and down. And this kind of gives an outline. You want to read through it of the different modes that are available. I have put in here the different ladder diagram instructions. So here's our load not, ands, and nots, ors, or nots, outputs, output nots. This one's interesting. They call it a differentiate up and down. This would be like a one-shot rising in an Allen Bradley or falling. So these are like one shots. They only compute one time. So it's a one shot is what it is. And I did actually see quite a few of these in the PLC I got off eBay. We'll see how many they have in the other one, but it's the reason I put it here and bring it up is just because it's differentiate up and down. It's not typical of what I'm familiar with, right? It's one shot rising or one shot pulse in an Allen Bradley. This just shows another the ladder diagram instructions, and at least here you can see the actual instructions in the end. So I guess that's why I put it here. Is you're looking for this one is using that one shot rising. So when we have that first input on, it's using that 22,500, and you can see it in the second rung here, 2550. That's going to initiate this move instruction. So that's why that's somewhat relevant to what we're looking at, because you'll be able to see it in here. And if we see that one shot rising, it's probably used somewhere else. You can see it's loaded on that next line right there. And it helps with the execution of the instruction itself. This is in the appendix. And I'll attach the manual for you guys if you would love to spend some time reading. But this is what's important to us. This will be what we'll need to look at when we're decoding, so we can see what each symbol and mnemonic name correspond to, right? So when we have counters, this is our counters, our loads, load nots, timers, because all we'll be able to see is the mnemonic code, right? We won't be able to see the symbol or the function. That's what we'll be translating. Here's some more, your end instructions, failures, counters. And this is what I was getting at is although this unit's very outdated and old, it's way more complex and capable than the previous unit that we went over 2 weeks ago. Way more capable. The amount of instruction types and different things that you can do in it is fairly impressive. You have word shifts, binary conversions, arithmetics, word corrections, increments, display messages, long messages. So for a 32-bit word, subtracts, multiplies, just so many more capabilities in this unit block compares. And like I said, hopefully, you know, I know we don't have RS-232 outs and things like that. We're probably not going to be using a lot of this stuff, but we need to be able to reference it if we do see it and know what it's supposed to look like or what it's supposed to do. 1-digit shifts, move bits, like I said, they're just, it goes on and on with the capabilities here. And that's the last page of that. So, possibilities, we'll be able to decode from a 2-inch by 1/2-inch LCD. It's going to be super exciting. This is going over the memory areas in our appendix. So this is yet again our internal relays, special relays, auxiliaries. This is just breaking it down again to see, because we're going to need to know the acronyms, and then if the acronyms don't exist like they were saying, we're going to need to know what words and bits correspond to that. I brought up our word allocations again in our C28H and first expansion and second expansion unit, which I went over in the first part. Here's our data conversion table for our hex and binary and decimal. And this is the table we'll be using. It's a little more colorful in my Excel file, but we'll start at 0 and we'll start. This is actually a running program in the current one that I'm looking at. So we'll basically just write down our instructions, and you can see here where on 5, I'm going to out. That would be the end of my rung, and I'm starting here again on load not. So that, to me, we might put a space in between here or highlight it to separate our rungs, but this is what it's going to look like. And we'll just fill it out in Excel one by one, and then we'll decode it into actual ladder. I'm gonna open it for questions. That's the end of the presentation.
So that means basically when you're evaluating this program, you got to do it from that small LCD and then type it in your Excel with your laptop right next to you.
Correct.
Oh, wow. Do you know how many lines of code there are in that?
I do not, and I do not. We're gonna find out on Tuesday. That's the kind of the reason I need to come out now, is I needed everyone to get an understanding of what we got to do, and then I need to come out and see how many lines we have. It'll give me a better baseline for how long it's going to take to translate it. I'm about halfway through the Google translation right now for programming. I want to have that ready by Friday of next week, if not sooner. And then, you know, the OMRON PLC, let me just stop this here.